In today's lecture, we're going to talk about measures of central tendency, that's section 12.2, and then measures of dispersion, which is 12.3. So both of these fall in our category of statistics, which we started looking at last week and we're continuing with this week. So measures of central tendency is just a fancy way of saying, can we find the middle of the data? Or another word we often use is the average. And so we're looking at different ways of finding that middle or average of the data. And the one that most people are the most familiar with is what we usually mean when we say the average, and it is the mean. And what we do is we take all of the data and add up all of the numbers that we collected, and then we count how many data items we had, and we divide by that number. And so the formula looks like this. This little funky looking E is actually a Greek letter S. It's pronounced sigma. It's the uppercase Greek sigma. And it stands in math for sum. So take the sum of all of the X values, all of the data items that we collected, and then divide by N, which is the number of data items that we collected. Let's look at an example. Here we have a graph which shows from 1980, almost every 5 years, because it ends in 2019, but almost every 5 years, we have the price of a movie ticket for those 9 different years from 1980 running up through 2019. So from $2.69 in 1980 all the way up to $9.16. And these are the averages. So the average US price. So theoretically, you figure out what every movie theater is costing in the US in 1980, find the average, that gives you this value of $2.69. And then we could also figure out what's the average over these 9 different years that we've collected data for. So to figure out the average price between 1980 and 2019, we could add each of these. So 269, 355, etc. Add up all of these numbers on top of the bars. And then since we have 9 years that we're looking at, we would divide by 9. And that's how we would use this equation. The notation that we use for the mean is this X with a bar over it, and we just literally say X bar, and that is the mean. So here's all those prices. I added them all up, and then I divide by 9, and I get $5.79. One thing to really pay attention to if you're going to do this with a calculator is to make sure that you have parentheses. So if you're entering this into a calculator, remember our order of operations, if we don't put parentheses here, then the calculator is going to add all of these numbers, and then at the very end, it would only divide the $9.16 by 9 if I don't put those parentheses around it when I do the calculator. So we would end up with a really large number, which would hopefully suggest to you that something was off. But you can see that the average of all of these is $5.79, which makes sense because it's in between the lowest value of $2.69 and the highest value of $9.16. And it's kind of in the middle of the data, which is what I would expect from an average. Now, sometimes we have what we call a frequency distribution. Let's look at the next slide so you can see an example here. So I have these various stress ratings from 0 to 10. And the data that was collected was that students were asked, well, how would you rate your stress level over the last 2.5 weeks on a scale of 0, no stress, to 10, the highest possible stress. And you can see that these answers range from 0 to 10. So what this tells me is 2 people had a stress level of 0. 1 person had a stress level of 1. 14 people had a stress level of 10, and 31 people had a stress level of 7. So if I wanted to find the average of these, when I was collecting the data, my raw data, before I put it into this table format, would have looked something like this. I would have had 0 twice. I would have had 1. I would have had 2 3 times. I would have had 3 12 times, and so forth. So when I want to find the average of all of this, to figure out how many students I spoke with, I need to add up all of these numbers. So we can write that with that sigma. Sigma F would tell me how many students in all there were. And then what I want to do, instead of adding 0 plus 0 plus 1 plus 2 plus 2 plus 2, is I can multiply each of these. Okay, because I have 18 fives, which is 5 times 18. So I'm going to multiply all of these, which would give me some values over here. I'll write the first couple. So let's see, 0 times 2, 1 times 1, 2 times 3, 3 times 12, and so forth. And then I'm going to add all of these values up. So I'm going to add all of these x times f values that I found. And now that means the mean is going to be the sum of all of those x times f values that I found over here, divided by the sum of the frequencies, how many students I spoke to. And on the next slide, we have what that looks like. Whoops. Okay, so here's all of those values that we calculated. Then we're going to add all of those up and divide by the sum of the frequencies. So here's what that equation is going to look like. So if I add up all of these values, I get 975. If I add up all the frequencies, I get 151. And then when I divide them, I get 6.46. And again, just looking at the ratings went from 0 to 10. And they were kind of centered, clustered about the middle or towards the high end. And so 6.46 seems like a reasonable answer. If my answer was something like 11, I would be very suspicious since the ratings only go up to 10. So I would expect it to be somewhere between 0 and 10. The next way of finding the average that we're going to look at is called the median. And the way most people learn to distinguish this one is that the word median sort of looks like the word middle. Same number of letters. They both start with an M and have a D in the middle. And the median is basically just that. It's the middle of the data. Now, when you're calculating a median, you want to make sure that you first arrange the data items in order. Okay, they have to be ordered. If I have the data items 1, 10, 7, the middle value is not 10. I would first reorder them 1, 7, 10. And now you can see that the middle value is 7. So this step is very important. Make sure that you order them. If we have an odd number of data items like we had here, then the middle is going to be the exact middle because you're going to have the same number on either side of that middle. If you have an even number, though, let's look at this example. If we add 6 in there, okay, now I have 4, so there isn't a middle. The middle's here. When I have an even number, what I do is I take these two numbers that are on either side of the middle and I find their mean, which remember, the mean is just add them up. There's 2 of them, so I divide by 2. And I get 6.5, exactly halfway in the middle. An important thing that you probably noticed here is that the median isn't necessarily one of the numbers in the list, right? So here it's exactly one of the numbers in the list. Here, the median doesn't show up in the list. The mean also doesn't typically show up in the list, does it? If we think back about the means that we calculated in previous slides. Also, not usually, doesn't have to be one of the data items. Let's look at this example. So again, the first thing I notice is that these aren't in order, right? 88 is smaller than all 3 of these numbers. 95 is smaller than 98. So I'm going to reorder them. And then once I've reordered them, there's 5 of them. That's an odd number. And that means that the middle item is the median, 90. And if you're doing one of these quickly on paper, a quick way to make sure that you get them in the right order is to just start with what you think is the smallest. So I kind of scan them and go, okay, I think this looks like the smallest value, 84, but I leave some room in case I'm wrong. And then I say, okay, 88 looks next. And then I kind of scan them, okay, 90, and I'm crossing them off as I go. 95, and then 98, crossing them off as I go to make sure that I don't write anything down twice and I don't skip anything. And then now that I want to find the middle, so I've got them in order and I want the middle, I cross one from the front, one from the back, one from the front, one from the back. And when I get down to only having one or two in the middle, if there's one in the middle, that's my median. If there's two in the middle, then I average them, find the mean, and that's my median. So for this data set, again, if we look at it, we can see that it's not in order. Here's 7, the smallest data item, and 74, the biggest. And they're right next to each other in the middle of the data, so that's not right. So I would do that procedure that we did on the other slide, put them in order. And now if I want to start counting them off, I see 1 in the front, 1 in the back, 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 and I'm left with 2 values in the middle. So I'm going to find their mean, add them up, divide by 2, and you can see that 31 is the median, right in the middle of those 2 values. That's the way I do it if I have a small number of data items. It's usually easier to just figure it out by hand. If I have a lot of data, then I might want to use technology, and we will take a look at using Desmos to calculate some of these things. Let's look at how we would find the median if we have one of those frequency distributions again. So here's that data with the, let's see, 151 different stress ratings. So 151 students asked what their stress rating was. We have the ratings from 0 to 10 and the number of students that answered that particular level. So to find the median, what I first need to do is figure out how many data items there are, which we've already done. We added up these frequencies and we got 151. So the middle value would be whatever's in the position that's half of 151. And so we have to add 151 plus 1, which gives us 152, divide by 2. So the 76th position, there would be 75 values below it, and then 75 values above it. Another way of thinking about this is you've got the 1st through 75th positions, then you've got the 76th position, and then you've got the 77th through 151st. So there's 75 numbers here, 75 numbers here. Whatever's in the 76th place in order is the median value. And then what I do is I count through here. So you can see there's 2 here. 2 plus 1 is 3. So in the 3rd position would be a 1. 3 plus 3 is 6. So in the 6th position would be a 2. And then I keep adding 6 and 12, 18 and 16, 34 and 18, 52 and 13, and 65 and 31. And I can stop now because you can see that there's a 6th in the 65th position. And then in the 66th position, we start coming in here and get our 7s. And there's a 7 in position 66 through 96, which means that in the 76th position, we would also have a 7. And another way is just imagining again that what this data would look like. 2, 2, 1, sorry, 0, 0, 1, 2, 2, 2, 12 threes, 16 fours, and so forth. And so if we counted through all those when we got to 76, we would be on a 7. All right, let's talk about comparing the median and the mean. So in this example, we have the salaries of 5 different employees in a television manufacturing company. And so their salaries range from 29,700 to 33,000. And then we also have a 6th person who is the manager who earns a salary of $105,000. So if we calculate the median, we can put those in order. So here's those 6 salaries in order. And notice that we would have 2 numbers in the middle, since there are 6 of them. So to find the median, I'm just going to add these 2 values, 31,500 plus 32,600, divide by 2, and I get a median salary of 32,050. That's the median. If I want to calculate the mean, I have to add up those 6 salaries and divide by 6. So I'm going to add all 6 of them. When I divide by 6, I get 43,700. And remember that the median was 32,000, roughly. The mean is 43,000. So what happened? Why are they so different? 32,050, I think, was the median. So here's the median, and here's the mean. Well, what happened was this value here, when we calculate the mean, we have to include this value in the calculation, and that makes the mean much bigger than, or seem much bigger than it really is. So whenever we have what we call, or whenever we have a very high number or a very low number, we call it an outlier. Whenever we have one of these outliers, we usually prefer to talk about the median because it gives us a much better value, right? The average salary really isn't 43,700 because all 5 of these people have a salary below that value. So this value, calling this the average, makes a lot more sense. And that's why we talk about both the mean and the median, and we're often interested in comparing them. The last one we're going to look at is the mode. This is the data value that occurs most often. And we often use this when we have data that doesn't have any numeric value, like eye color. So I might count people who have various eye colors. And I can't really average brown and black and green and hazel and blue and gray. So what I would do if I wanted to say the average, I would just report whichever eye color showed up the most frequently. And notice that while middle and median sort of look alike, mode sort of looks like the word most. So the mode reports whatever shows up the most. The other thing to keep in mind is that data doesn't have to have a mode. So if I have values 10, 15, and 20, there's no mode. On the other hand, if my data values are 10, 10, 22, 22, 30, I have 2 modes. So both 10 and 22 are modes. I can have as many modes as I like or no modes. For this data, and it often helps to put these in order as well, just to help you kind of see what the duplicates are. So often when we're calculating a median, we're also calculating a mode. So once we've got the data ordered, it's easier to kind of see which one shows up the most frequently. We also sometimes talk about the mid-range. So what is the middle of the high and the low values? So for the mid-range, all you do is figure out the lowest data value, that should be data, not date, the highest data value, add them, divide by 2. It's just the average of the lowest value and the highest value. All right, so let's look at this example. We have the best places to be a woman with the score. So it looks like Iceland. I think I'll stick with living in the US and not having freezing cold and dark for a lot of the year. And then we've got on the other side the worst places to be a woman. So I probably am not interested in visiting some of those countries. I like being treated well. Let's see. So best places to be a woman. We want to find the mid-range for these. So if we're only looking at the best places, we want to see what the mid-range score is. We just take the high score, which is 100. The lowest of just these scores, which is 87.2, add them up, divide by 2. So we get a mid-range for the best places to be a woman of 96.6. That's pretty good. All right, we're going to look at the next section, which is going to be, where did we go here? Here we go. 12.3. So we've talked about finding the middle of the data. We also like to talk about where or how spread out the data is. So what did I do here? All right, let's try this again. I think I did that wrong. How about that? That seems like it worked. Okay. Let me just start the slideshow so we get a better view of these. So how spread out the data is what we call dispersion, measures of dispersion. And we use this to talk about, it's nice to know what the middle is, but we also want to know, like, is all the data kind of towards the middle, or is there a big, wide range of values? Both measures of the center and measures of the dispersion kind of help us summarize what's going on in the data. So the easiest, most simple way of figuring out what the spread is to just take the high value, the low value, and subtract them. So for example, in Honolulu, the hottest day of the year is 89, the coldest day is 61. So the range in temperature is 89 minus 61, 28 degrees. Okay. This, while easy, is also kind of the least informative. Okay, because kind of like what we were talking about with those salaries, if we took the range is pretty big between those 5 employees that all had a salary of around 30,000 and then the manager who had a salary of over 100,000. So the range would be pretty big, like 60 or $70,000. But that doesn't really give us that much information because those 5 salaries were all really close together. And then we have that one outlier. So we usually like to get more information, but this is a good quick way and easy to calculate. So let's talk about finding what we call the standard deviation. And what the standard deviation is it first calculates the mean. So that center piece of the data where we add up all the data points and divide by how many there are. And then it looks at for each data item, how far away is it from the mean? So for example, if I have these 4 data items, if I add them up, divide by 4, I get 1.89. That makes sense. The mean is right here in the middle. So between the lowest and the highest values. So what I'm going to do then is I'm going to take each data item and then subtract the mean. So the first data item was 1.17. I subtract 1.89 and I get 0.72 and so forth. So here are all of so this value is 72 points below the mean, 72 100ths below the mean, 37 hundredths below, 90 hundredths above, and 19 hundredths above. And notice that your first thought might be, let's just add them all up and we'll know what the deviation is. But notice if we add up those numbers, They all cancel each other out, don't they? Because we're comparing them all to the mean, and the mean is the average of all of them. So these all add up to 0. So what we do instead is we say, what if we squared these values? And then we can divide by the number of values that there are, and then we can take the square root at the end. And that's exactly what we do. The difference is that we actually have 2 different ways of calculating the standard deviation that's a little bit beyond the scope of this text and what we're doing in this class. But depending on whether we're talking about the entire population or just a sample of the population, we either divide by n minus 1, which is for a sample, or n, which is the population size for a population standard deviation. So in this class, we're just going to be focusing on the standard deviation of a sample. So we just have a subset of the data from some population. And so, as I said before, we take each data item, subtract the mean, square it, add those all up, divide by 1 less than the number of data items, and then we take the square root so that we're back into the original units. So this is what the formula looks like for standard deviation. And that's a lot of steps. Fortunately, in the modern world, we have technology to do that. So I'll show you how you can do that in Desmos. All right, so the standard deviation for gasoline prices. So here we have gasoline prices, definitely not in California, but somewhere. So in 1990, $1.17. So every 10 years from 1990 to 2020. And so we could add these, divide by 4, and we would find the mean to be $1.89. Yep, right there in the middle. And then here are those deviations. And then we're going to square each of them. So over here, I've got the difference between each data value and the mean. And then here I have the square of that. And then I'm going to add up all of these values. And then I'm going to divide that by 1 less than the number of data values. So 4 minus 1, or 3. And then I'm going to take the square root. So the standard deviation is 0.71. And what that tells me is that most of the data is 71 cents on either side of the mean. And it tells me actually a lot more that's beyond the scope of this class, but if you take a statistics class, then you will study all of those things. The next thing that I want to look at is, let's see here, using Desmos to calculate some of these things. And let's see, first of all, okay. Let me share my Desmos with you. Okay. Here we go. So we are looking at the Desmos calculator. So we've used this a little bit, and I'm actually using the Desmos graphing calculator, but you could also do this with the scientific calculator. And so for the first example, I love this example. I actually learned about this little urban legend, which I think is mostly true, from another statistics book. So apparently Michael Jordan, when he first graduated from the University of North Carolina, he had a geography degree. And someone, a cab driver, actually met him, someone who was giving him a ride, and said, oh, you know, I was a student also at the University of North Carolina studying geography, and I got so fired up because the professor told us that the average starting salary for graduates was $250,000. And this was back in 1986. Michael Jordan graduated from UNC in 1986. That would have been a lot of money in 1986. And then the driver said, well, we later figured out that he was counting you because Michael Jordan was a geography major. So if we take a look in Desmos, at the cell, and I'm just assuming that I'm keeping it small so you can kind of see what's going on here. So assume that we had Michael Jordan, who's his first year out of college, he made 630,000, which again, doesn't sound like a lot of money, but in 1986, that was better than what most geography majors got. So we have someone who got 17,000 and someone else who got 18,000. So here's the list with Michael Jordan, and look at the mean. The mean, if we include Michael Jordan and these two other people who got just regular standard salaries, the average salary does look like about 225,000, pretty close. If we take the mean without Michael Jordan, look at that, 17,500. Okay. So again, whenever we have one really big or really high value, we prefer to talk about the median. Let's look at the median. I can do the same thing, median with Jordan, 18,000. And what is going on here? Oh, okay. And the median without Jordan. So the median doesn't change a whole lot, does it? That outlier has practically no impact on the median, but a huge impact on the mean. And so how do we use Desmos then to find all of these fun values? Let me see, actually, I am going to change my share one more time. So that I can put Desmos next to some of the problems from our book that I want to look at. So let me get that set up and then I'll reshare the screen. Okay. All right. Let's get this one up now. Okay, so get rid of some of these means and medians. So for the statistics that we'll be doing in this class, the formulas are pretty straightforward. Let me just show you what this looks like if we use the scientific, which is the one that is linked in your exams. Okay, so here's what the function looks, or the calculator looks like. We can still do all of those things. We just don't get we don't see the graph. If you forget what the functions are, you can always click over here on function. And that will show you the various functions that are available. So mean, standard deviation, and this is the standard deviation that we're going to use. Okay. So in the first example that I wanted to do, I'm going to look at number 38 here. Okay. So I've got these values and I want to find the mid-range. So 11, 6, 4, 0, 2, 1, 12, and 0. So first I have to identify the smallest of those data points. And that looks like it's going to be 0. Hold on one second. I need to get my pencil back working again. There we go. Okay. So the smallest value is going to be 0. And then of these values over here, the largest is 12. So the mid-range is just going to be 12 minus 0. Okay. So that seems like a pretty good range of data, doesn't it? If I wanted to find the mean and the median for that data, I can just type in mean and then I can type in the list of data. So I don't even have to order it 11, 6, 4, and sometimes you can even copy paste it. It doesn't work great with a PDF. So you can see the mean is 4.375. And then I can also calculate the standard deviation. And I can type that in again. I can copy and paste it. Okay. So standard deviation is 4.8971, or usually we keep one decimal place when we just have one or two decimal places. So 4.9. The other thing that I can do, like I had done in that previous example, is I can do something like this, and I can say data is equal to, and then type in all of those data items. And then I can say take the mean of that data list that I gave you. Oops, I did the wrong thing here. Not parentheses, brackets. There we go. That's why it gave me an error. So whenever you have a little exclamation point here, it means you did something wrong. So that's what I did wrong. I accidentally typed in parentheses. For a data list, it wants brackets here. So then I can just say take the mean of that list and then take the standard deviation of that list. And will it let me do the median? Yep. And the median. Nope. Doesn't like that one. Oh, this calculator doesn't do the median. Sorry, we got to do that one by hand. Or you can use the other calculator. Let's see what else we have. We did the mid-range. Oh, I'm on the wrong page. What I wanted to be on. Let's go to 823. Okay, yes, I love this question. Okay, 38. So we have these, let me see, can I make that a little bit bigger? So we can see, oh, that's better. Okay, so we have the age of the first 6 US presidents here, at which time they were inaugurated, and then the last 6 US presidents over here. And the question is, just looking at them, which one do you think has the greater standard deviation? So if I just look, these all seem to be grouped in the high 50s and low 60s. So I would say there's not much deviation, is there? The smallest is 57, the largest is 61. So even just the range is pretty small. And they're all kind of clustered in that same area. Now these, look at, we've got Obama who was only 47, and then Biden who was 78. So quite a range there. So just from looking at the data, you can kind of get an idea of what do you think the difference might be. And then let's look. So we'll just call the first set F for first. Oh no, it probably doesn't want me to do that. We'll do P1 for the first presidents. And then the data set was 57, 61, 57, 57, 58, 57. Okay, and then we can find the mean. Oops, forgot the equal sign here. No, I don't want that. Okay, so yeah, the average age is basically 58. Okay, and then I'm going to do P2 for the other list of presidents' ages. And we have 64, 46, 54, 47, 70, 78. And the mean, oops, of those is 59, or almost 60. So means are pretty similar, aren't they? But let's look at the standard deviation. The standard deviation for the first one is only 1.6 years. So on average, most of the presidents, the first 6 presidents, were within a couple years of age 57 when they were inaugurated. Whereas on average, the last 6 presidents have been within 12 years of that middle age of 50, 60. So you can see much more deviation there. And then let's see. Oops, I did not want to do that. Let me go back. I hit the wrong button. Okay. I wanted to look at this problem over here, number 40. Why the range might not be the best measure of dispersion. So when you see a question like this one, kind of think about what your answer would be first, because these, when they show up on your homework, they're usually multiple choice. So if we think back to this question again, the range for this one would be, let's see, 4. We said the range was 4. Okay, so that shows me that there's not a lot of dispersion. Whereas the range for this one is higher. So for these data sets, sure, makes sense. But let's think back again to when we were talking about a data set that looks like this one. We'll call it T. Okay. So the mid-range there is 18. That looks like just a crazy amount of dispersion, right? But if I look at the standard deviation, you can see that it's 6.9, okay? Which shows me that most of the data is within 7 points of one another, which is true. So we can still see that there's a lot of spread, but it just doesn't really give us quite as much information. It's a good kind of first pass. Another way of thinking about it is it just gives us the difference between the first and the largest. So let's look at this one again, this data set T, and then I'm going to have a data set S. And now, whoops, these data points are going to be 0 0.2, 0 0.3, 0 0.3, and then 2. Okay, so you can see here that the range now is only 1.8, whereas in data set T, it's 18. Okay. But in terms of the standard deviation compared to the values, the deviation is very similar. So range also kind of depends on the size of your data points. You know, are the numbers large, like 20 million, 30 million? That would be a very different look than what we have here. So a couple of different reasons. What else did I want to look at? Okay, this is a true or false. I'm working with data sets with the same mean and different standard deviations. Could that be possible? So a good way to answer a question like that is to kind of think about, well, what would that look like if I had data that had the same standard deviation but different means? That seems entirely possible, doesn't it? Because they're measuring two different things. The mean is telling me what's the middle of the data, and the standard deviation is telling me how spread out the data is. So they're both important pieces of information, but they're completely different. Okay. And then let's take a look at this question. So we're going to use this data here. So I'm going to, whoops. So we're looking at problem 54. And I'm going to enter that data set over here. I'm going to call it data set 1 and see if it will let me copy. Let's try it. Oh, so sometimes we get lucky. Nope, it didn't. It copied something. It kept what I had copied earlier. Okay, 0, 1, 3, 4, 4, 6. Okay. So there's that data. And the standard deviation of this data set. Oops, hit the wrong button. is 2.1. So on average, all of my values are within 2 points of the mean. And then let's do the second data set. We're going to add 2 to each of those. So 0 plus 2 is 2. 1 plus 2 is 3. 3 plus 2, 5. 4 plus 2, 4 plus 2, 6 plus 2. And then, okay. So, look at that. Doesn't do anything, does it? Because we added 2 to all of the values. I think that's the end of what, yes, that is what I had for this week. So next week in our live lecture, we will be doing a review for the final.